So our today topic is the last topic of this semester, and it's the impulse and momentum of rigid bodies. Before the midterm, we study something about the relationship between the impulse and momentum for particle. So for particle is mainly we consider, we have the linear momentum and angular momentum for particle, but particle don't have the dimension. So maybe we mainly consider the translation of particle. But in this case, for today's class, we are going to apply the impulse momentum equation to describe rotation of rigid body. And rotation of rigid body. And also, like, we still need to consider the effect of the translation of some particle in the system also, and it will affect the total linear momentum, total angular momentum of the system. And we will see the application on the rigid body. And we have some example that describe the different phenomena. And I hope from the example we can see, like, we can get better picture on how to apply the impulse and momentum in the problem. Before we jump into the example, we may need to have a short derivation on the equation of the impulse and momentum. In this slide, we are talking about the derivation to the impulse momentum equation for linear motion. For linear motion means we only consider the rigid body that have only the velocity vector at the center of gravity, but omega gonna be 0 for the linear. No, not like that. I'm sorry. For the linear impulse and momentum equation, it's not talking about the rigid body that is not rotate. I'm sorry, but we are going to relate the summation of force to the rate of change of the linear momentum. It's Newton's second law. Newton's second law of motion. Okay, so this schematic will be used in both cases, both the linear relationship and the angular relationship. So let's see the picture. This rigid body has the center of gravity at point G. And with respect to the global frame's origin, we have the vector that describe the position of point G. G is the center of gravity. R bar vector, if we have bar, if you still remember from the last lecture, if we have R, if we have bar, we are talking about the thing that relate to the center of gravity or point G. The position vector of point G is R bar vector. The velocity vector of point G is V bar. And V bar is the first time derivative of R bar vector. V bar is the first time derivative of R bar vector. So at the center of gravity, we have the velocity vector, and the rigid body also rotate with omega. At any particle of mass on rigid body, that particle may have the mass of mi, which is the mass of the I particle, and the position vector of that particle with respect to the global frame's origin is described by the vector Ri. Is the position vector of the mass mi with respect to the global frame. And in the rigid body, we have the vector rho of particle I. The vector rho describes the relative position of the mass with respect to the point G. Rho is the relative position vector of the mass with respect to point G. So we can see that here the position vector of the particle I may be formed from the position vector of the center of gravity, and the relative position vector. We may write it like this. But what I want to say is what should be the velocity vector of point I? What should be the velocity vector of point I? The velocity vector of point I can be composed from the velocity vector of the center of gravity and the relative velocity of point I with respect to the center of gravity. If you see the picture, the same vector of V bar, if we only consider the effect of translation, the velocity vector of point G, we slide to here, and the vector have the same magnitude and same direction at that point. It means we apply the translation effect of the center of gravity in all the points on the rigid body. They should have this component of velocity. In any point of rigid body, they should have this component of the V bar. But the velocity that depend on the position, the velocity vector that depend on the position of the mass with respect to point G will be this one. The rigid body has omega. And the relative position vector rho I. Omega cross rho I. With this magnitude of omega, the direction of omega now is point out from the the screen. No, point into the screen by the right hand rule. Point into the screen by the right hand rule. So by use the omega crossed by the relative position, we're gonna have the relative velocity that perpendicular to the direction of the radius, the relative velocity that perpendicular to the direction of the radius, and the magnitude of the relative velocity is equal to the magnitude of the omega multiplied by the perpendicular distance here, or the magnitude of the law. The momentum, linear momentum of the mass mi, the linear momentum of the mass mi as a particle, the mass mi, the linear momentum of the small mass mi is equal to the mass of particle I and multiply by the velocity vector of that particle I. And velocity vector of the particle I is equal to the first time derivative of the position vector of that particle. The total linear momentum is the sum of the individual point linear momentum. The sum of the linear momentum is the sum of mi and vector vi for all particle on the rigid body. So it seems like we are going to have the sum, the first time derivative of the sum of mi ri. We are going to have the time derivative of the sum of mi ri, and by the definition of the r bar vector, r bar vector is the position of the center of gravity. This is equal to 1 per mass of summation mi ri. The position of the center of gravity is equal to the summation of small mass multiplied by the position vector. The total sum of this, when we divide by the total mass, we will have the r bar vector. You may familiar with the form that the center of mass in the x direction is equal to 1 per total mass of summation mi xi ycm equal to 1 per the total mass multiplied by the summation of the small mass mi yi. Here is the scalar form But for the vector form, the position vector of the center of gravity is 1 per the total mass and multiplied by the summation MIRI. So it means that this one, we can see the summation of MIRI. This summation of MIRI, we can consider it as the mass, the total mass of the rigid body, and multiply by the position vector of the CG. The position vector of the CG. So mass is not changed against time. Mass is not changed against time. So the rate of change of the R bar vector, the rate of change of the R bar vector can be considered as the velocity of the CG. Velocity of the CG. So what I'm going to say here is the total momentum of rigid body. The total momentum of rigid body is equal to the mass of the rigid body multiplied by the velocity vector of the CG. The CG can represent the rigid body for the linear momentum. The velocity of the CG can represent a rotating rigid body. No matter how fast it rotates, or not rotate, but if it have the velocity vector of the CG, the linear momentum is non-zero. If we have V bar. And yeah, from the Newton's second law of motion, the summation of force that apply around the rigid body, the summation of force that apply on the rigid body will equal to the summation of the change in the linear momentum in all small particles. The effect of the force that apply on rigid body will appear as the acceleration of the small particle. The summation of force that apply on rigid body will equal to the effect on the acceleration of the small particle. And when we sum the MA of all the particle, it should equal to the summation of force that apply on the rigid body. And with the same consideration here, the summation of small mass with acceleration AI, it can be represented by the total mass of rigid body, multiplied by the linear acceleration of the CG. Bar means we are talking about the acceleration of the CG. We can write it as the d by dt of the mv bar. d by dt of mv bar. When mass is constant, d by dt of mv bar when mass is constant is equal to ma. So if we have the integral of the summation of force with dt, it will equal to the change in mv bar vector. This means if we have the summation of force and integral force dt is impulse, linear impulse. The linear impulse is equal to the change of the linear momentum. Change of linear momentum. The linear impulse integral f dt equal to the change delta of the linear momentum. The linear momentum is represented by the vector g, So the summary is here. The vector g, linear momentum of rigid body, is equal to the mass of rigid body multiplied by the v bar vector. And summation of force that apply on the rigid body is equal to the rate of change of the linear momentum, And this relationship is the Newton's second law of motion. The summation of force equal to the rate of change of the linear momentum. And this is the impulse momentum equation. It means the impulse from time t1 to t2, the initial linear momentum, add by the effect of the impulse, we will have the final state linear momentum. So yeah, or we can say that the linear impulse is equal to the difference between the final state and initial state of the linear momentum. So yeah, in this slide, we explain the concept of the linear impulse and momentum. How about the angular momentum? Angular momentum and angular impulse. We're gonna begin with the relative velocity relationship. Velocity of any point I on rigid body is equal to the velocity vector v bar of the center of gravity and plus by the effect of the rotation, in the relative velocity of that point I with respect to point G. Relative velocity of point I with respect to point G. If we consider the direction from the picture, it seems like V bar has the direction in the horizontal direction, like this. And the direction of the relative velocity, if you can see here, yeah, it has the direction, the inclined direction like this. The magnitude, how about the magnitude? The magnitude of V bar is V bar. The magnitude of the relative velocity, the magnitude of the relative velocity is equal to the magnitude of the relative position vector rho I and multiplied by omega. The relative velocity here has the magnitude of the rho dot vector, magnitude of the rho dot vector is equal to the magnitude of the omega multiplied by the magnitude of the rho. So here is the relationship of the velocity to the velocity at the CG and the relative velocity. If we talk about momentum, of course, momentum of any individual particle will have the direction and have the magnitude. The magnitude is equal to mv bar and have the rho dot omega, and it should be multiplied by the mass of that individual particle, the mass of that individual particle. Angular momentum. What is angular momentum? Angular momentum. The angular momentum here, if you see the linear momentum, they write in the vector form. But in this slide, for the angular momentum, we are writing in the scalar form. We just consider the direction, positive and negative, because this rigid body is moving on a plane. So if we consider the angular momentum about the CG, angular momentum about the CG of any individual particle, angular momentum about CG of any individual particle with the mass mi. So the effect of the horizontal V bar, the effect of the V bar on the angular momentum, it depends on this perpendicular offset. The V bar create the angular momentum about point G. If we set the clockwise direction to be positive, the effect of this on the angular momentum will be the magnitude of the mv bar multiplied by the perpendicular offset. we're gonna set the beta angle here to explain. The beta angle is the angle that the relative position vector make with the vertical direction, In this case, the effect of mv bar that create the angular momentum is equal to the MIV bar multiplied by this distance rho I cosine beta, and create the clockwise angular momentum. MIV bar multiplied by rho I cosine beta is the linear momentum of a small particle with the v bar velocity and create the angular momentum about point G in the clockwise direction with this magnitude. How about another component of the velocity, the relative velocity? The relative velocity with the magnitude of omega rho I always make the 90-degree angle with the offset here. So the effect of this relative velocity on the angular momentum will equal to the magnitude of the linear momentum mi and rho I omega. Rho I omega is the magnitude of the relative velocity. Mi is the mass of the small particle. And here is the linear momentum. If we want to obtain the angular momentum, we need to multiply by the distance, the orthogonal distance. This orthogonal distance has the magnitude of rho I. So yes, we can rewrite this by, we have mi v bar rho I cosine beta plus mi rho I dot square omega. This is the angular momentum of a small particle. What is the total? Angular momentum about the CG? We need to sum all the angular momentum. Of any small particle. So for the sum, what we're gonna have is for this one, we have V bar constant, and we have the summation of mi rho I cosine beta for the first term. For the second term, omega is constant, but we need to have the summation of mi rho I square, and omega is equal for all the particles. If you still remember from from the previous lecture, the rho I cosine beta. This seems to be the vertical displacement or yi. So the summation of mi yi, the summation of mi yi about the center of gravity, summation mi yi about the center of gravity is equal to zero, because for the center of gravity, we have mass above the center of gravity and we have the mass below the center of gravity. When we obtain the summation of mi yi, the sum will equal to zero for this. How about the summation of mi rho I square? If you still remember, it equal to the I bar, or the moment of inertia about the point G, the moment of inertia about point G. So the angular momentum about point G, you may write hg or h bar is the angular momentum about point G. It equal to the moment of inertia about the CG multiplied by the angular velocity. For the linear momentum is the mass multiplied by the velocity vector. Mass is the inertia property. Mass is inertia property. For the angular momentum, we also have the moment of inertia multiplied by the velocity, angular velocity. So momentum is the inertia multiplied by the velocity. We may have heard that the momentum indicate the, the motion property. So momentum is the product of the inertia and the velocity. And the next derivation should be the Newton's second law. This is the step of the velocity. How about the acceleration? I'm sorry. Y is I bar equal to mi. Okay. The moment of inertia is equal to the integral of r squared dm. The moment of inertia is equal to the integral of r squared dm, or the moment of inertia may equal to the summation of mi ri square. This is the definition. If you have one single point here, at point O, and you have the mass m1, and the mass m1 has the radius r1 measured from point O, and if you have another mass if you have another mass, it's gonna be maybe m2, and mass m2 has the distance r2 from the point O. The moment of inertia about point O in this example, it's gonna be equal to mass 1 multiplied by the radius 1 square plus by mass 2 multiplied by the radius 2 square. So this is the definition of the moment of inertia about any point O. When the mass here is the discrete, I mean the mass is the finite mass that we know the mass and can find the exact radius, we're gonna use this summation here. But in many cases, we have the continuous mass. For example, if you want to obtain the moment of inertia of this rotating disc, you may need to perform the integration to obtain the moment of inertia about point O. So to answer your question, why this one is equal to I bar? Actually, the summation mi rho I square is defined as the moment of inertia, but for here, the rho I is measured with respect to the point G. Is measured with respect to the point G. So now we are talking about the moment of inertia about point G. So we have the bar that represent, we are talking about the moment of inertia about point G. So we have I bar here. Okay, come back to if the force vector, we need to consider the mass mi. If the mass mi has the acceleration vector ai, if the mass mi has the acceleration vector ai, we should have the summation of force that apply on, we should have the summation of force that apply on that small particle as Fi. Of course, we may have many force apply on the rigid body, and the summation of the total force in the different position will create the force between the particle. And of course, if we want this small particle to have the acceleration vector ai, and that particle has the mass mi, we should have the force that apply on that small particle defined by Fi. In this step, we talk about the relative velocity. What about the relative acceleration of the point I? The acceleration vector of any point I can be obtained from the acceleration of the center of gravity. We come back to this picture. You see that for the velocity, the relative velocity here, have only one direction. It's perpendicular to the radius, perpendicular to the radius. The relative velocity perpendicular to the radius. But if you still remember, if we talk about the acceleration, about the CG, we may have two possible directions. We may have two possible directions of the relative acceleration. The first direction will be the tangential direction. And the second direction of the relative acceleration will be the normal. Here, the tangential acceleration, A, I per G in tangent direction, depend on the direction of the alpha. If alpha is clockwise direction, the tangential acceleration will go upward like this, and perpendicular to the radius is tangent acceleration. If alpha is counterclockwise, the direction of the tangential acceleration will go downward, but still perpendicular to the radius. So in this case, let's assume alpha is clockwise. The tangential acceleration perpendicular to the rho. The normal acceleration is not depend on the direction of alpha, not depend on the direction of omega, but the normal acceleration always point to the center. So in this picture, A bar, or the acceleration of the CG, may have some linear acceleration in any possible direction. It may have the same direction with V bar, or may have different direction with V bar, but they have the direction of A bar. The magnitude of A bar vector is A bar. The magnitude of the tangential acceleration depends on the magnitude of the radius multiplied by the magnitude of the alpha. Alpha r, alpha rho will be the magnitude of the tangential acceleration. For the normal acceleration, omega square r, the magnitude will be rho I, and omega square will be the magnitude of the normal acceleration. So if we write MAI vector, it means we are writing the, we just multiply this by AI. So all the terms here, the three different terms, will be multiplied by MIA bar vector, plus MI rho I alpha vector with the direction of the tangential, and mi rho I omega square in the direction of normal direction. This is the force vector that should be applied on a small particle. The force vector that should be applied on a small particle, so that we have the mass multiplied by the acceleration vector. The force that applied on a small particle should be formed from this relationship. But we know that the moment is the force multiplied by the radius. Moment m is the force multiplied by the radius. For here, I write m as scalar. So it means, yeah, we are going to take the clockwise as positive. And if we see the effect of the force in the first component here, the second and the third component here, the moment about point G, of any individual particle I, the moment about point G of any individual particle I is equal to the force magnitude multiplied by the radius. In this case, if the A bar has the same magnitude with the V bar, the radius gonna be rho I cosine beta. The radius gonna be rho I cosine beta. For the tangential force, the magnitude of the tangential force is mi rho I alpha. The radius between the tangential force and the center G is the magnitude of rho I. So if we have the force, tangential force, the moment will be the force multiplied by the radius rho I, because it's always perpendicular between the tangential and the radius. But for the normal force, the centrifugal force here, the direction of the centrifugal force is passed through the point G. So this component of force doesn't create the moment about point G. So the third term, it will create the zero moment. If we want to obtain the total moment about point G, is equal to the sum of the moment about point G of the individual mass I. That means we need to sum this term and sum this term for all the mass. For this one, A bar is constant, and we have sum of mi rho I cosine beta. For this one, alpha is equal for all the particle. Alpha is equal for all the particle. We have the sum of mi rho I square. We have the sum of mi rho I square. So again, we use the same reason. This one is yi, and the summation mi is equal to 0. Summation of mi is equal to 0. For the second term, we have alpha, and the summation of mi rho I square. The summation of mi rho I square is the moment of inertia about the center of gravity. So yes, here we relate the moment about the center of gravity. The moment, the sum of the moment about the center of gravity is equal to I bar, or the moment of inertia about the center of gravity, multiplied by the alpha, and similar to the linear impulse and momentum relationship, similar to the linear impulse and momentum relationship. Yeah, you may write the summation of moment equal to the I bar d omega by dt, I bar d omega by dt. But I bar omega is h bar. I bar omega is the angular momentum. We also can relate the summation of moment. The summation of moment equal to the rate of change of the angular momentum. And here is the angular impulse. Angular impulse also affect the change in the angular momentum. Linear impulse affect the change in the linear momentum. Angular impulse, the integral of moment dt, affect the change in the angular momentum. And the angular momentum is the inertia, moment of inertia, multiplied by the angular velocity. Linear momentum is the mass or the inertia property multiplied by the velocity. And another view to describe the problem. Now we derive the thing with respect to the center of gravity at point G, center of gravity at point G. But of course, in many applications, we may consider the angular momentum about a certain point O. Point O can be any point that we can know the information in the problem, and easy to compute the summation of moment about point O. Easy to compute the inertia about that point. So for the general plane motion, we can obtain the angular acceleration about point G, or we can obtain the angular momentum about point O for the general plane motion. If we consider the angular momentum about point O instead of the point G, what we need to do is, hey, the angular momentum about point G, we still have this effect about the different reference point. We still have this effect of the angular momentum about the new reference point, but we need to add the effect of the linear momentum. We need to add the effect of the linear momentum multiplied by the orthogonal distance d that the linear momentum at point G make with the new reference point O. So the the angular momentum about point O. Before this, if we consider the point G, as reference, the angular momentum about point G is simple, is equal to the I bar, or the moment of inertia about point G, and multiplied by omega. But if our reference point is changed from the center of gravity G to any point O, the angular momentum is computed from the angular momentum about point G plus by the magnitude of the linear momentum, multiplied by the orthogonal offset, to create the HO that positive in the clockwise direction. Here, for the general plane motion, we have two possible choices. We may consider the angular momentum about point G if it's simple, or if point O is easier by the given information from the problem, we may use this relationship. How about if point O is fixed? If point O is fixed, we only try to obtain the moment of inertia about point O and multiply by omega. So if we apply this to this for general point O, what's gonna happen is point O equal to I bar omega plus m v bar multiplied by the offset d, right? So here we have I bar omega. If we have the fixed point O, we can relate the magnitude of the v by r bar. V equal to r bar omega. V equal to r bar omega, because we have the fixed point and r bar is fixed. R bar is the radius or the distance between point O and the center of gravity. R bar is the distance between the fixed point, fixed axis rotation, and the center of gravity. And the orthogonal distance d What do you mean by fixed point O? Okay, fixed point O means the velocity of point O equal to 0. The point O here, the rigid body is pinned. The rigid body is pinned on a support. We cannot have the displacement at point O of the rigid body. The rigid body can rotate, but the velocity of point O always be 0. It doesn't move. So here, the orthogonal distance D in this case is equal to the distance between point G and point O. So what we can see here is we have the common term omega. We have the common term omega. We have I bar plus M R bar square and omega. So the angular momentum about point O now is equal to I bar, or the moment of inertia about CG, and mr square, and multiply by omega. If you have any particle, any rigid body, and you know the moment of inertia about the CG of that rigid body, if you want to change the position to be the different point, if you want to change the position to be the different point, the moment of inertia about the new point will equal to the I bar plus by the mass of the rigid body and multiply by the distance between the new point and the point G square. For example, I think you may be familiar with this case. If you have a bar fixed for fixed O, yes, this can be applied only for the fixed axis rotation. Actually, it's not that constraint. I mean, actually this can be applied for general plane motion. This can be applied for general plane motion. Point O in the left cannot be. Okay, this is the answer to direct message from Daoput. For any case, actually, we can apply this relationship. We can apply this relationship to the general plane motion. General plane motion means we may have the fixed O or not fixed O, but the I of any point equal to the I about the center of gravity plus by mr square is still true. I think you may be familiar with this. If you have a bar with the length L and the mass M, if you have a bar with the length L and the mass M, the axis of rotation may be like this. You have the bar with the mass M and length L, the I bar of this case is equal to 1/12 ml squared. The I bar for this case is equal to 1/12 ml squared for a slender bar. If you change the axis of rotation to consider the moment of inertia about this point instead, what's gonna happen for the moment of inertia about point O? by apply this relationship, if you want to obtain the moment of inertia at the left end of the bar instead of the CG of the bar, you're gonna have the I bar first by the mass and this offset square. This offset is L/2. This offset is L/2. If the length of the bar is L, this offset measure between point G and the left end of the bar will be L/2 square. So what should be the new moment of inertia about point O? What should be the new moment of inertia about point O? We're gonna have 1/12 plus 1/4 of ml square. 1/12 plus m/4. What do we have? So if you have now, maybe can anybody, no. I want you, all of us, to check this together. Can all of you open the video to talk to me? The person who's still in the class now, please turn on your video. Not sure if you can, but can you find a ruler on your table? Can you find a ruler or a pen on your table? Can you find ruler or pen on your table? That's one thing. Show me your ruler or your pen. Show me on the screen. Can you show me? Okay. In the beginning, grasp your pen in the middle. Grasp your pen in the middle. Grasp your pen in the middle of the pen. Middle, like this. Use one hand. Contact the pen with one point. You see my hand? Yes, grasp your pen here. Now you grasp your pen at the center of gravity of the pen. You grasp your pen at the center of gravity of your pen. You try to rotate your pen. You try to rotate your pen like this. It's easy to do, right? It's easy to do. It's easy to do. You can easily change the rotation of your pen. If you touch your pen at the center of gravity, you can easily rotate your pen when you touch your pen on the center of gravity. The second case, move your hand to another end of the pen. Move your hand to another end of the pen. Can you still do this? Yes. try to do the same thing. Try to change the rotation of the pen. I think now you can feel, you can tell me what is your feeling. Is easier or harder than the previous case? We begin from Dauput. Dauput, please turn on your microphone.
It's harder than the first case.
Okay, this one in the center of gravity is the first case. And then we have the second case. We rotate it at the end of the pen. In your opinion, which one is harder? Use your feeling. Which one is harder? The second case. Okay, and Eisen also have the same answer. Okay, thank you for your participation. You can turn off your video. I will too. And we come back to the lesson. Okay. Okay, Eisen and Dauput has the same answer. If we try to rotate the bar at one end of the bar, what you did is, in the previous case, you rotate the pen about its CG. In the second case, you try to rotate the pen from the different point. So what I'm going to say is, in the first case, I bar is equal to 1/12 ml square, approximately. In the second case, I about 0.0 is equal to 1/3 of ml square. So yes, by the feeling, you can see some difference. Actually, it's a huge difference. It's a huge difference. If you change the position, you can see the huge difference in the inertia property. In the first case, I bar is the inertia property to resist the motion, the rotation. I, moment of inertia, resist rotation. It means moment is equal to d by dt of I omega. Moment is equal to d by dt of I omega. If I is constant property, moment will affect the change of omega by dt. If you rotating the thing at the CG, you have I bar. But if you change the position that you try to rotate it, you perform it with IO. And in general, every time at the center of gravity, the object will have the minimum moment of inertia. Minimum. When we change the position, we need to increase the effect of the offset. The effect of the offset. And we will increase the moment of inertia. Okay, the first example, do you need break or I can continue? So we will continue. Okay, this example is not difficult. We begin with, we have the bullet. We have the bullet with the mass 28 gram. And the bullet travel with the velocity, and the bullet hit with the pendulum, After that, the bullet will stay in the pendulum and create the omega of the pendulum, And the problem also give the information of the distance h. The distance h means we know the offset between the linear momentum and the center. The problem also give the position of the CG. The CG have the offset 825 millimeter far away from point O. But they give another information, radius of gyration. Wait. Radius of gyration here. The radius of gyration about point O. Okay, the radius of gyration about point O here. The meaning here is when you need to obtain the moment of inertia about the CG, and the problem give the mass and the radius of gyration. The moment of inertia about the CG is equal to the mass multiplied by the radius of gyration square. If we need to obtain the moment of inertia about any point, if the problem gives the radius of gyration about that point, we can simply obtain the moment of inertia about that point by directly multiply the square of the radius of gyration to the mass. In this case, the pendulum is a compound pendulum. Compound pendulum means it's not in a simple shape. It has the combination of this part and the slender part. And the problem don't want us to compute I/O by ourselves. They give the simple information, radius of gyration, and we can compute the I/O by this information. So the problem give the mass of the bullet 28 gram, and the problem give the speed of the bullet 500 meters per second, and the problem give the mass of the compound pendulum and give the radius of gyration of the compound pendulum about point O. radius of gyration about point O. And they give the information of the distance h, 1075 millimeter. What we need to find is the omega of the pendulum immediately after the impact. It means immediately after the bullet is embedded inside the pendulum, it will create the rotation. Of the whole system. In the beginning, just the bullet has the velocity, but omega equal to 0, and the pendulum doesn't move. After that, when the bullet is embedded in the pendulum, it creates initial rotation to the pendulum. What should be the omega after the impact, after the bullet hit with the pendulum? So we have before and after case. Before means if you see here the pendulum have point O, and have this offset h. We may have mg. If we draw the free body diagram, we may have mg, we may have oy, we may have ox force at the support. I'm going to draw a free body diagram of a pendulum. Pendulum has a support force at point O in x direction and in y direction. The pendulum has mg. Force applied at point G. They have only this force applied on it. And we have the bullet, but the bullet still not apply force to the pendulum. My question is, what is the magnitude of the angular momentum about point O? What is the magnitude of the angular momentum about point O? In this case, in the initial case, we have nothing move in the system. We only have the bullet that move. The bullet move with magnitude mv, and the orthogonal distance h. So at the initial condition, the angular momentum about point O is equal to mv h, and mass is 0.028, v is 500, h is 1.075 meter, and this gonna equal to what should be the unit of the angular momentum? HOI means angular momentum about point O at initial condition. Initial condition. What should be the unit? What should be the unit of angular momentum? We have kilogram. We have meter per sec. And we have meter. So the unit will be kilogram meter square per sec. Now the direction of this is clockwise direction. At the initial condition, before the impact of the bullet, we have the angular momentum about point O obtained by the linear momentum magnitude multiplied by the orthogonal distance. And what is after the impact? After the impact, we still have the compound pendulum, and it's embedded by a bullet. We still have the force. And mg increased to be m plus mg because the mass of the compound pendulum is added by the mass of the bullet, so the mass increased. What is the angular momentum about point O after the impact? Angular momentum of point O after the impact. After the impact, we don't know how it's gonna rotate. What should be the initial omega? The omega is still unknown. But if we consider only the pendulum has the moment of inertia. It should have the omega after the impact, but we still don't know that omega. And the bullet that embedded in the pendulum, in the initial, the bullet has velocity v, but after that, we don't know the velocity of the bullet. But it still keep the line with the perpendicular distance h. It still keep the line with the perpendicular distance h. What should be the relationship between the velocity after the impact and the omega? When the bullet embedded in the pendulum, it's gonna have the velocity to be v plumb. How can we relate v plumb to the unknown omega? V prime equal to the omega multiplied by the radius. V prime equal to the omega multiplied by the radius. And the moment of inertia can be obtained from the radius of gyration. So the angular momentum at the final state, is equal to I-O omega plus by m h square omega. And it seems like now we know everything. I-O is equal to m. I-O, I'm sorry here to avoid confusion. M is the mass. Wait a second. Why my screen sharing is paused? Okay, now I think you still can see my screen, right? Okay. Come back. To avoid confusion, the moment of inertia is obtained from the mass of the pendulum multiplied by the radius of gyration. The mass of the pendulum multiplied by the radius of gyration square. This is I-O. And mass of the bullet multiplied by the distance, orthogonal distance from point O square, and omega. I think we know everything in here. We know the mass, 25 kilogram. Radius of gyration, 0.925 square. Mass of the bullet, 0.028 kilogram. Distance h, 1.075 square. And the whole thing will multiply by omega. And the numerical value in the parents is 21.423 omega. So the angular momentum about point O at final condition and at initial condition. Why I need to draw the free body diagram? I want you to check the impulse momentum equation. The summation, the integral, this should be better. The integral of the summation moment about point O dt. This is the angular impulse. This term is angular impulse. It's equal to the change in the angular momentum. Angular impulse is obtained from the summation of moment about point O and integral by dt. If you see the free body diagram at the initial state, the force mg, the force ox and oy at the support pass through the point O. The moment will be zero until the final state. We have only the force that pass through point O. The moment always be zero before the pendulum change the angle. We cannot see the effect of mg to create the moment about point O. So it means in this case, the angular impulse is equal to zero. Angular impulse is equal to zero. So yes, the angular momentum at final state and angular momentum at initial state should equal. And this is the first equation. This is the second equation. Make it equal. Angular impulse at initial state equal to, angular momentum at initial state equal to angular momentum at final state. We can solve for the initial omega after the impact. The numerical value and yeah, the direction of the omega will be clockwise direction. This is the first example.
Excuse me?
Yes.
Could you describe the radius of gyration again? I mean, like how it can be used to calculate the moment of inertia regardless of its shape?
Okay. Yeah, because you may. Okay. Maybe in the real application, for example, you design maybe robot link with complicated shape. Maybe if we want to know the effect, the inertia property of the robot arm, maybe your robot arm may be some like this, and you want to know the inertia effect about the rotational axis of your robot arm in this axis. In the experiment, you may try to mount the robot arm with the rotational actuator and try to rotate. When you know the torque, and you can measure the angular acceleration, you have one blank thing here. And this one blank thing should be the moment of inertia about the rotational axis. So in this problem, they can give you two possible information. The first way, they may just tell you that, hey, this compound pendulum has moment of inertia about 0.0 equal to something. They may just give this information, but they don't want to give you in this way, give you information in this way. They give you the mass and give you the radius of gyration. But when you work in the future, if you need to deal with this type of problem and you know the information from the data sheet or the catalog of the physical part of the mechanical part, please remember that they may give you the information of mass and the moment of inertia about x-axis, about y-axis, about z-axis, or they may give you the radius of gyration about that axis. But as a user, to use that information, you can compute the radius of gyration. No, you can compute the moment of inertia from just the mass multiplied by the radius of gyration square. Why this concept come from? Where this concept come from? This concept come from, hey, if you have one single point and you have one mass that travel about the single point, the mass has mass m. The radius between the mass and the center will be r. With this, if you have only one mass m and travel about the fixed point O, the moment of inertia about point O is equal to m r square, which means we know only the mass and know only the radius, which is the distance between the fixed point and the mass. We can obtain the moment of inertia about point O. But for a complicated shape, if we neglect the mass of this part, we only have the mass in this part. The radius of gyration may be extend to somewhere around here, and the I about O is equal to the mass of the pendulum multiplied by the radius of gyration square. But with the compound pendulum, you cannot neglect the mass of this component. The mass of this component still affect the total moment of inertia. So maybe the radius of gyration here, of course, is bigger than the distance from O to G, but it's less than the distance H is somewhere here, because we still need to consider the effect of the inertia in this part. Yeah, something like this. Is it clear?
So it's like, it is like a general value that's used with the like I is equal to mr squared to simplify the calculation, right?
Yes. So if you know the mass m, if you know radius of gyration k, you can compute I by m k square.
And the way to obtain it is by like a back substitution of m I over m.
Yes.
Oh, okay.
Yeah.
So basically, it's like a floating value that like remove us from calculating some messy fractions.
Yeah. Yeah,
So,
yeah.
okay, I think I understand now. Thank you.
Okay. Okay, the second problem here. The second problem here. Do we need break? Okay, so just keep going. In this system, they have two components in the system. The first one is a pulley here, a pulley. And the second one is a mass here. The mass is hang to the center of the pulley. The mass is hang to the center of pulley. And the pulley is driven by cable. We have two cables that connect to the pulley. And these two cables has different force magnitude. Has different force magnitude. But these two cables has the same direction. It's going upward. It's going upward. Can you imagine what's gonna happen with this system? What's gonna happen with this system? We only have the force, two force in the upward direction, and we have the mg. We have the mg, and we have the mg. It means we have the mg of the 20 kilogram load, and we have the mg of the pulley itself in the downward direction. But we have the force in the upward direction. So yeah, when we check the magnitude of the force in the upward and downward direction, we can obtain the acceleration or the velocity of the whole system. But if we check the moment, the summation of moment about the rotational axis of the pulley, the summation of moment seems to be like non-zero, which means it's gonna create the angular acceleration in the pulley. In the initial condition, the pulley itself and the load already have the velocity, and the load has the velocity. The load has the velocity 2 Newton meter downward. No, 2 meter per sec. Sorry, what? 2 meter per sec in downward direction. And the pulley itself has the angular velocity in the counterclockwise. And this happened in the initial state at time t equal to 0. They want us to find, hey, after the time passed by 5 seconds, after the time passed by 5 seconds, what should be the velocity of the whole system, the linear velocity of the whole system in upward, downward direction, and what should be the omega at final state. But the important information is the magnitude of force always constant, 200 and 160 Newton. The magnitude of force always constant against the delta t of 5 seconds. So we have the force 200 Newton and the force 160 Newton constant, and initial speed 2 meters per second in the downward direction. Initial omega is 8 radian per second in the counterclockwise direction at t equal to 0. And the duration that we consider, the delta t, equal to the t final subtract by t initial, equal to 5 seconds. And what we need to find is the velocity at final and the omega at final condition after 5 seconds. After 5 seconds. So let's see let's draw the free body diagram. The free body diagram. We have the pulley and it's connected to the load, right? We have the force in upward direction, 160 Newton, 200 Newton. And we have the mg of the wheel, the pulley. mg is 15 g. And at the load, we have 20 kilogram multiplied by g. From the impulse and momentum equation, the integral of summation of force by dt will equal to the change in linear momentum. Let's set the upward direction be positive. Let's set the upward direction be positive. We know that the force always constant. The force always constant against delta t. Force always constant against delta t. So the integral can be the sum of the force and multiplied by delta t. It can be summation of force and multiplied by delta t. So summation of force from the free body diagram, upward force will be 200 Newton, 160 Newton. Downward will be 20 G and 15 G. And delta t is 5 seconds. This should equal to the mass, total mass, multiplied by V final and V initial. V final and V initial. The total mass of the system will be 20 kilogram plus by 15 kilogram. The, how to say, the thing we should concern is the direction of the velocity, direction of velocity. We don't know after the situation what should be the direction of the velocity. In the initial condition, the velocity is downward. In the initial condition, the velocity is downward. We still don't know the velocity final is gonna upward or downward. But yeah, we can assume it to be upward or downward first. In this case, I assume the final velocity to be downward with the magnitude of Vf. How this assumption affect our equation? In the equation, when we consider the force, we set the upward direction to be positive. We set the upward direction to be positive. But we set the upward direction to be positive for the impulse momentum relationship, but the direction of final velocity that we assume, the final velocity has downward direction with magnitude Vf. That is still unknown. How about the initial velocity? The initial velocity, we know the magnitude, and the direction is given, is downward. So the downward direction is minus magnitude 2. Be careful. This direction is defined. We define this direction to compute the impulse momentum equation. Everything that upward will be positive. The upward force positive, the downward force negative. So we need to be careful about the given speed and the unknown speed. In this case, if you assume Vf to be upward with the magnitude Vf, you don't need to put minus here. You just have the magnitude Vf. But now we don't know it's gonna going up or down, but I assume it's going down to be positive. It means if we compute Vf and its positive value here, the direction that we assume is correct. If we compute the numerical value and it's negative, it means the actual direction of final speed should be in the opposite direction. So solving this equation, the numerical value will be negative. Minus 0.379 meter per second. What does it mean by the negative magnitude here? It means that the actual direction, it should be the upward direction. It should be the upward direction. How about the angular impulse and momentum? angular impulse and momentum. The integral of summation m dt should equal to the change in the angular momentum. The change in angular momentum. Let's set the clockwise to be positive. Let's set the clockwise to be positive. The summation of moment about point O. This is a vector equation. This is scalar equation. The rotation is considered on a plane. It's considered on a plane. We have only positive and negative. In the clockwise, counterclockwise is is rotation on a plane, on a single plane. So we consider the moment equation as a scalar equation. The summation of moment about point O. The summation of moment about point O. The mg pass through point O, not create any moment. 200 Newton with the radius create the clockwise moment, the positive moment. The radius 0.3 meter. 160 Newton create the counterclockwise moment. And the magnitude of the summation of moment always constant. The magnitude here always constant against the delta t. So don't forget to multiply the delta t here. The impulse equal to the change in the angular momentum. Delta h about point O equal to moment of inertia of the rotating part multiplied by the delta of the omega, the delta of the omega. So IO, moment of inertia about point O, is obtained by m of the pulley multiplied by k bar square from this given information. K bar means the radius of gyration. Radius of gyration about CG. K bar is radius of gyration about CG. But luckily for the pulley, the CG and point O are the same. Are the same point. The CG and point O of pulley are the same point. So the mass of the pulley 50 kilogram, radius of gyration 0.25 meter square, and delta omega, the final omega, I assume omega final to be in the clockwise direction. I assume omega final to be in the clockwise direction. So when I set the governing equation, I define the positive direction to be on the clockwise So omega final, magnitude, and unknown. Positive in the clockwise direction. Omega initial is 8 radian per sec. Omega initial is 8 radian per sec in the counterclockwise. So counterclockwise is minus. So yeah, again, by solving this equation, we have omega final. And the omega final, the numerical value is 656 radian per sec. And it's positive. So the direction that we assume to be the clockwise direction is correct. Okay, and we are going to have the next example as the last example for today. So here is the last example. Here is the last example. The conservation of angular momentum. Yeah, we may be familiar with this type of problem in maybe physics class or many class. It's not difficult, but in the schematic here, they draw the picture in 3D. And don't be afraid of the 3D schematic of the picture. Try to simplify the picture. What does it mean by simplify the picture? Before that, let's check what is this problem. We have the base B with the mass 5 kilogram, the base B. The blue part has mass of 5 kilogram. And again, radius of gyration. Radius of gyration about this axis. Central vertical axis. Because now the part B is rotating about this axis. They give the information of the radius of gyration so that we can compute the moment of inertia of part B about this axis. And they give another example, another information. The plate B has mass of 3 kilogram. The plate P, we have two of plate P with the mass of 3 kilogram. And the whole system begin from this posture. The plate P lie in the vertical direction. And the plate P has the dimension shown here. It has the length 300 millimeter, have the CG at the center, have the CG of the plate at the center. And this depth information. And they also give the dimension of the B base. What happened is in the initial condition, the plate P lie in the vertical orientation like this, and the initial speed of rotation is like this. And then by the gravity, the plate move downward to the datum position like here, and cannot go anymore because we have the stopper here. It just can lie on the horizontal plane. The question is, after it moved to the final state, what should be the new angular speed of the rotation? the new angular speed of the rotation. So if I'm going to draw this picture in 2D, if I'm going to draw this picture in 2D, we have the base B with the rotational axis, and we have the plate in the vertical direction. At the initial condition, the plate lies on vertical direction like this, but at the final state, it's flipped to the final orientation like this. What happened is it's gonna change the rotational speed from N1 to N2. Why? It needs to change the rotational speed. Because in this system, we have mg of the base. We may have mg of the plate. Until here, we have the mg of the plate. At the center of gravity of the plate, we have mpg. But we know that the axis of rotation is in the vertical direction. And the mg always parallel to the axis of rotation. Mg always parallel to the axis of rotation. And we cannot obtain the component of mg that create the change in the angular velocity. We're gonna have the component of force that create the change in angular velocity. If we have the force that can have the orthogonal distance from this on the plane of rotation. The plane of rotation is xy plane of rotation. Of course, this mg may create the moment about the point here, but it's not on the plane of rotation. It's not on the plane of rotation. So yes, in this case, the problem, okay, we come back to the given. They give the mass of the base B, 5 kilograms, with the radius of gyration of the base B, 80 millimeter. The plate P has the mass of 3 kilograms. The plate P has the mass of 3 kilograms. And N1 is 10 revolution per minute. What we need to find is N2. The impulse momentum equation integral of summation moment dt. Integral of summation moment dt will equal to the delta of the angular momentum, delta of the angular momentum. But as I mentioned that the summation of the moment, the force never create the moment about the axis of rotation. The force never create the moment about the axis of rotation. The angular impulse in this case will be 0, and the angular momentum as final state will equal to the angular momentum at the initial state. And we need to check what is the angular momentum at the initial state. Angular momentum at the initial state equal to the moment of inertia at initial state multiplied by the omega at initial state. The moment of inertia, if we see this picture, the moment of inertia about the axis of rotation, the axis of rotation is this one, right? The moment of inertia about the axis of rotation should come from the inertia property of the base frame, and the inertia property of the plate. So let's see the center of gravity of the base frame in the original orientation. The center of gravity of the base frame is lie on the axis of the rotation, and the center of gravity of the plate is here, which means we have the distance here between the mass of the plate P at the center of gravity and the axis of rotation, So the first part of the moment of inertia comes from the mass of the base B multiplied by the radius of gyration about the central vertical axis, The central vertical axis of the base B in this case is the same with the axis of the rotation. So we can directly use the radius of gyration because the rotational axis and this position is already the same position. For the effect of inertia due to the plate, we have two plates, and each plate has mass m of the plate. And in the original posture, the radius that the plate far away from the center of rotation, this distance is 120 millimeter. So the mass MP with the radius 120 millimeter will create the moment of inertia for the plate, mr square. M is the mass of the plate at the center of gravity. R is the radius measured from the axis of rotation to the position of the mass MP. And these are the moment of inertia at the zero, at the initial condition. And the speed at the initial condition, the speed is 10 n1 equal to 10 rev per minute. We have 2 pi radian per 1 rev, and we have 1 minute equal to 60 seconds. So it means if we want to turn the rev per minute to the radian per sec, we need to multiply by 2 pi per 60. 2 pi per 60. And by substitute the known information, the mass of the base 5 kilogram, radius of gyration 0.08 square, and 2 of the mass of the plate 3 kilogram, and the distance from the center, the plate have 120 millimeter distance from the axis of the rotation square, and 10 and 2 pi per 60. So the numerical value of the terms in the parent is 0.1184 multiplied by 10 multiplied by 2 pi per 60. This is the initial angular momentum about maybe here. I'm gonna set O here and O prime here to indicate the axis of rotation. Maybe in this case, if I say about O, maybe you cannot get a clear picture on where is O on here. But if I describe the axis of rotation by O prime, O like O prime, it should be better. Here also will be O to O prime at final and at initial. Here is O to O prime at initial condition. Moment of inertia I is also the I of O to O prime axis. If we give only the point O, you can get only point, but if I say O to O prime, I hope you can get the meaning that O to O prime is a line. The axis is this line. It's not a single point O. Okay, for the final condition, the angular momentum of O to O prime, angular momentum around the axis O to O prime at final condition is equal to the moment of inertia O to O prime final multiplied by the second omega. So the moment of inertia will be the mass of the base and the same radius of gyration. Only one thing changed compared to the initial condition will be the distance. Only one thing changed from the initial case will be the distance of the mass of the plate from the axis of rotation. In the initial case, the distance will be 120. But in the second case, after it changed, the distance will be this distance, which means you need to have 120 plus by this distance. The plate itself has the total length of 300 millimeter. So the CG position is 150 millimeter measured from the edge of the plate. So here will be the half width of the base, 0.12 meter, plus by the half width of the plate, 0.15 meter square. And this will be multiplied by omega 2. Omega 2, the problem asks for N2, not omega 2. So omega 2 can be N2 and multiplied by the conversion factor, 2 pi divided by 60. And the numerical value here, MB 5, radius of gyration 0.0x square, 2 of mass of the plate 3, and the final distance here will be 0.27 square, and N2 is unknown, and the conversion factor, and the numerical value in the parents is 0.4694 multiplied by N2 and the conversion factor. And yeah, you know that this one, initial condition, initial of the angular momentum is equal to the final state angular momentum. So yeah, you can solve for N2. For me, I got N2 equal to 2.62 ref per minute. Compared to the original one, before it's changed, the posture at the initial posture is rotated with 10 ref per minute. But after it changed the posture, it's increased the radius. So it seems to be like makes sense that it decreased the angular speed. So yes, that's all for today. Do you have any question? Okay, so I'm gonna think about the exam and the assignment, and I will put the explanation to the exam and the assignment by this Saturday. And what I ask you to do is discuss among your friends to set the examination date for me and let me know. So thank you very much.